Let's take a look and see how these are going for you. The first one here, finding the missing dimensions. This is a skill that we find is getting more and more difficult. It's just not, as people do less and less with their hand and more on a computer screen, it's just something we've lost. And this, of course, is not an easy example of it either. But to find missing dimensions, let's pick out dimension A here. Since that's a horizontal dimension, we can only use other horizontal dimensions. So that means we can use 12 here, 18, 16, 6, 24, and 4. Those are the only dimensions we can use associated with A because they go in the same direction, same orientation. To find that, there's a lot of different strategies we can use. One of them is to look for things that have to add up to the same length. Well, that's not quite so easy here because things kind of double back on themselves. If we just had a simple notch out of the corner of a rectangle like this, like we did as an example last week, if you have 20 feet here and let's go 13 feet here, you can very easily find this missing dimension because the 13 plus the missing dimension has to add up to the 20. It's not quite that straightforward here. So another strategy that can be used is to just set a reference line and go by the distance away from that reference line. The reference line has to go in the opposite orientation or perpendicular to the lines we are working with. So I might just put a reference line right here. And then every point as I go through is referencing a distance from that line. Like this here is 12 feet from that reference line. This here is still 12 feet. It hasn't moved at all. Here, it's an additional 18 feet. So 12 plus 18 makes that point 30 feet away from the line. How far is this point away from the line? 46. Good. This point? Still 46. Hasn't moved at all. How about this one? Back to 40. This one? Still 40. This one? Careful. You've got the right idea. There it is, 16. 40 minus 24 gives us 16. So of course that's still 16. How about this one? 20. 16 plus 4 is 20. So that is 20. So A covers that whole distance. A has to be 20 feet. For B, B goes vertically. So we can only use other vertical dimensions. I'm going to erase my reference line here. So we can only use these dimensions associated with B. Now B is actually probably a little bit easier to find here. I'm going to use a reference line. Now let's just go down here. Actually, B is one I could just add them up. Let's do it just to show you a second way of doing it. Let's just do it that way. We know that these green lines here go all the way from top to bottom. These green lines here go all the way from top to bottom. So they have to add up to the same thing. So we have 18 and 12 here. That adds up to 30. Perfect. Going this way, we've got 4, 6, 8, B, and 6. So 4, 6, 8, and 6. What do those add up to? 24. Good. Well, B has to be the difference between the 30 and the 24. So B is 6 feet. Good. Do those make sense? That is like I said, it's not an easy skill, and it's one that seems to be fading a little bit. So it's something to make sure you're good at. focusing on what dimensions go in the same direction, what dimensions affect each other. The second one here might be a little foreshadowing to a quiz coming up later. Looking at forming a concrete patio and sidewalk beside a house. So I don't know if you know much about concrete work, but you don't need to form up against the building. So the black line up here for the house, we don't need any forms for. The rest of it, the brown line around the outside, which I'll outline in blue here, you have to run forms all the way around it. For a sidewalk and patio, you typically only go 3 or 3.5 inches deep. So a 2x4 is adequate. So we need to find the length of that blue line, or that 2x4 form. Did anybody get an answer that they think is correct? Anybody want another minute or so to give it a shot? Okay. We'll give you another minute to work on that. Some of you might not be all the way done, but let's go ahead and take a look at what you've got so far. So we need to find some missing dimensions here as well. So let's find the dimensions that we do have. The 14 is going to be part of it. We're going to need 14 feet there. 20 is going to be part of it. So we'll add 20 feet in. This piece we're going to need to find. Well, if we look at it, it's 14 feet from here all the way down. This piece is 8 feet. This piece here is 4 feet wide for the width of the sidewalk. That's got to be 2. Very good. So we'll add in 2 feet for that. This across here is the 14. We need this distance. How long is that going to be? 12 feet. We could go about it 2 ways. You got 14 minus the 2, or you could get 8 plus 4. That's going to be the 12. Perfect. So now we're going to jump over to here. This piece has to be 8 feet. That forms a rectangle, so it's got to be the same as this piece over here. This piece is going to be across here. 10 feet, good. 14 feet across minus the 4 feet of the width of the sidewalk. And then finally, that one is 8 feet. So if we add those all up, it's not a very fun one, is it? Is that 28? I'm getting 88 feet. Does that sound right? Perfect. Any questions on any of those? What we had time to do for homework and what you managed to get done during the week. Did you have any questions off the homework from last week? A little bit, or? Okay. One of the weaknesses of that little book is it breaks it down almost too much. So you know that every question in one section is going to be addition, every question in the other one's subtraction. So that's a little bit of a drawback there, but it's still neat to have it in the context of construction. Well, so where we left off last week is we started talking about order of operations. those levels of priority, the enclosing symbols, exponents, multiplication, division, addition, subtraction. And we did a couple very simple examples. Well, I want to start off today with a little bit more difficult example, then work our way up to a few others, and then we'll get you guys doing some of them on your own. So the example I put up here has a little bit of everything in it. So remember, we go through our levels of priority. Highest priority is that enclosing symbols, which is usually parentheses. So in this problem, we have a set of parentheses right here. So we have to find its other end and we enclose it. That's the part that's being enclosed by the parentheses. So we have to focus on that part of it. Now inside there, order of operations still applies. So we look for more enclosing symbols. There aren't anymore. Then we go down to exponents. And I guess there's one in there. The 2 to the power of 3. Now we haven't really talked about exponents yet, but that's just 2 times 2 times 2, which is 8. There we go. So I replace that 2 to the 3rd power with an 8. Everything else in the problem has to be rewritten exactly how it is. So the way I usually do it is I put the piece that I'm combining in a box. Everything outside that box has to be rewritten. So I hit the box there, I jump over to the other side. Now I'm sure I mentioned last week that a lot of the mistakes that get made in these problems are in rewriting it. There are some shortcuts you can take, but until you get good at it, I warn against it just because, like I said, that's mainly when people make mistakes, is they try to skip steps or try to not have to rewrite the whole question every time. So we're still working inside the parentheses there. There's no more exponents. So we go down to the next level, multiplication and division. There are several of them here, and remember we said when there's more than one thing at the same level of priority, we go left to right. So going left to right here, we have 32 divided by 8, which is 4. So replace that with a 4, and again, we rewrite the rest of the problem. So we hit the edge of the box, we'll jump to the other side. So still inside the parentheses, we're still at multiplication and division. Going left to right, we have 4 times 6, which is 24. And once again, we rewrite the rest of the problem. Still inside the box, inside the parentheses, I should say, we have one more multiplication or division. This is the division. 24 divided by 12 is 2. Thank you. Now all that's left in that parentheses is addition. Actually, it's all subtraction. So we're going to go left to right. First, we have 19 minus 4, which is 15. Good. Next, we have the 15 minus 2, which is 13. And finally, 13 minus 9 makes 4. Good. I should put that in the box. Now we've reduced what's inside that enclosing symbol to a single number. So that means for parentheses especially, we can probably get rid of the parentheses. But we do have to check to make sure that it's not doing anything else. Parentheses is an enclosing symbol, but it also serves other functions. One of them that it's doing here is it signals multiplication. This is saying when there's a number outside the parentheses with no symbol there, that is saying multiplication. So we can remove those parentheses, but we have to make sure we put that symbol in to denote that multiplication. Other enclosing symbols have other things that they can mean. Parentheses even have some other things they can mean. That's just one of them. So now there's no more enclosing symbols, no more exponents. Multiplication, 3 times 4 is 12. We're down to just addition, so we're going to go left to right. 7 times 12, 19. And finally, 19 plus 5 is 24. That's it. Now, I realize that's a lot of writing, but it saves on mistakes to copy down that problem exactly each time. So this one's a little bit longer, not terrible. So our first level of priority, again, is enclosing symbols. Here we have several of them. Remember, whenever we have more than one thing at the same level of priority, we go left to right. So going left to right, this is the first parentheses we run into. We have to find its other end so that we know what it encloses. This one's facing the wrong way, so that can't be it. This one has to go back to that one, so that's not it. So we go all the way down here to find the other end of that parenthesis. So we start out working inside that brown section there. But in there, order of operations still applies. So we still are looking for enclosing symbols. And there's another one. There's another set of parentheses there. So we're going to narrow our view down to that green section. In there, again, still applying our order of operations. No more enclosing symbols. There is an exponent. What is 3 squared? 9. Perfect. So we rewrite the rest of that problem. I need to write shorter problems so I don't have to rewrite so much. Okay, so we're still inside that green section there, inside that inner set of parentheses. All that is left is the 17 minus 9, which is, careful, 8. There we go. Now I've reduced the parentheses to a single number. So in the same step here, I'm going to take out the parentheses. Is the parentheses doing anything else in this problem? There you go. It's signaling that multiplication there. So I have to make sure I put in that multiplication. So now that parentheses is gone. We're out to that larger set of parentheses, that brown section, if you will. In there are no other enclosing symbols. No more exponents. So we're down to multiplication and division. What do we do first? Multiplication. 2 times 8, which is 16. Next, still working inside that set of parentheses. The next piece, what's the next 2 numbers we combine? 4 times 3, which is 12. Good. What's the next 2 that we're going to combine? There you go. 12 divided by 6, which is 2. Good. Now there is no more multiplication or division inside that set of parentheses. And we are still staying inside that parentheses in the brown area there. So what do we have to do next there? The addition. 9 plus 16 makes 25. Good. Then of course next is the which is 23. We can take out that parentheses. Do we have to put anything else in there? There is multiplication that's going to have to go in there. Now that set of parentheses is done. We're back out to the bigger problem. There are other enclosing symbols. We have another set of parentheses. What's the first piece we have to do inside that set of parentheses? The 16 divided by 4, which is 4. Good. And of course, finally, in that parentheses, we have to do 5 minus 4, which is 1. Now, again, I've reduced that parentheses to a single number. Do I need to put anything in when I take out the parentheses? No. There's already an operation in front. There's the addition. There are no numbers outside the parentheses that would signal multiplication. So now there's no more enclosing symbols. No more exponents. We need to multiply the 2 times 23, which is 46. Now it's all addition, going left to right. 17 plus 46? 63, good. And of course, 63 plus 1 is 64. Look kind of ugly to begin with, but as long as you go step by step, everything kind of works out. A lot of writing though. Let's look at something set up a little bit different. Let's do this. Okay, so in a problem like this, the first thing we have to figure out is what does this line across here mean? It does mean division. It's called a fraction bar. And division is one of the things it means. It's also an enclosing symbol. It separates the top of the problem from the bottom of the problem. So it's saying we have to do each of those parts separately, then we can divide. So let's do the top first. I'll write it off to the side here so we have room to work on it. What are the first two numbers we need to combine there? 5 times 11, which is 55. What's next? 42 divided by 6 makes 7. Good. And then finally, 55 minus 7 is 48. So the top part of that reduces to 48. On bottom, we have some exponents. Which do you do first? Well, the square root and the powers happen at the same time, so we work left to right. So square root of 9 is 3. Now, the square root is similar to a parentheses. In fact, we're going to see in a little bit that it can be an enclosing symbol. There's a number outside that square root. So once we've calculated the square root, another purpose of the square root is signaling multiplication. So we have to put in multiplication there. That's 11 times 3. What's next? 5 squared makes 25. And then 11 times 3 is 33. And then we subtract. 33 minus 25 makes 8. So the bottom reduces to 8. We do 48 divided by 8 makes 6. Good. So that reduces to a 6. I realize I'm a couple minutes late on our break. We'll do one more example, then we'll take our break here. So here's the one I promised. We have that square root symbol there. But there's more than one thing inside that symbol. It becomes an enclosing symbol. It's separating that part from the rest of the problem. So we have to do what's inside the square root first. So inside here, what has to be done first? The exponent, 3 squared, which is 9. Good. What's next? 7 times 9 is 63. Good. And then 1 plus 63 is 64. Now, we've reduced that square root symbol down to a single number, which means we can get rid of it. We can do the square root. Now, we need to look at the rest of the problem to make sure there's nothing else with higher priority. And there's no other enclosing symbols in this problem. So we can do the square root. What is the square root of 64? 8. Good. Now, when we do the square root, just like parentheses, we said we have to look for other things that it's doing. And here it is signaling multiplication. What would be done next? 3 times 8 is 24, and then of course 11 plus 24 makes 35. Okay. So I went about 3 minutes long. It's 2:23. Let's come back at 2:33. Go ahead and take a short break. So that's kind of it for order of operations. The next thing we want to do is we want to look at the next form of numbers. And that, of course, is everybody's favorite, fractions. Hopefully we can make fractions not as difficult as what you've remembered of. So we talked about fractions having 2 parts. Just like any other number, count in the name. Of course, the top number is called the numerator. Good, I know what you meant. And we said that is the count. It's telling us that we have 3 of something here. The bottom number is called the denominator. We said that is the name. Just like having inches or pounds or cows. So a fraction is not 2 numbers, it's 1 number with 2 parts. So the first thing we need to explore is what does it mean to have a name of fourths? Well, the easiest way to do that is to go back to the old elementary school drawing of a pie or a pizza. Pretend that looks like a circle. When I draw, you're gonna have to do a lot of pretending because I'll put it bluntly, I suck at drawing. Fourths means that's cut into 4 equal pieces. Again, try to pretend those are equal. So there's 2 ways we can look at it. Either every whole object gets cut into 4 equal pieces, or you can look at it as it takes 4 pieces to make 1 whole object, whichever makes the most sense to you. And now, of course, the 3 means we have 3 of those pieces. So the first thing we need to be able to do is rename our fractions. Simplest way with this illustration is to take each of those pieces and cut it into smaller pieces. So let's cut each piece into 3 smaller equal pieces. Again, pretend these are equal. While you're at it, pretend my lines are straight. So now, if I count those around there, how many pieces do I have to make up the whole object? 12. Perfect. It was 4, but we cut each of them into 3 equal pieces. 4 times 3 makes 12. How many pieces do we have there in yellow? 9. We had 3, we cut each of them into 3 pieces. 3 times 3 makes 9. Do we have any more or less than we did before? No, we have exactly the same amount. 9/12 is exactly the same amount as 3/4. How were we able to make that change and that affect the amount? Well, it's because of this right here, that 3/3. The bottom 3 is telling us it takes 3 pieces to make a whole object. The top three says we have three pieces. In other words, that equals one whole object, or just one. Anytime we multiply or divide by one, it gives us the same value. It doesn't change the value, but it can change the appearance of it. This is what we call a unity fraction. It is a very powerful tool in math. We're going to use it in a couple of different forms today to rename fractions and to reduce fractions. But when we get into measurements and conversions, it's also used to convert measurements, to do dosage calculations in the medical fields, a lot of different things that it can be used for because it can change the appearance of a number without changing its value. Now in this example, I just kind of picked the three out of the air and used it. In most cases, we have to figure out what is being used, what is multiplying to rename that fraction. So if I have something like 2/5 and I want it to be renamed as 20ths, I have to figure out what I had to multiply the 5 by to turn it into 20. What is it? 4. 5 times 4 makes 20. So that means we have to do the exact same thing to the other part of the fraction. In this case, the numerator. 2 times 4 makes 8. Good. So 8/20ths has exactly the same value as 2/5. If I have 1/3 and I need to change that into 24ths, what am I going to have to multiply the 1 by? 8. There we go. 3 times 8 makes 24. 1 times 8 makes 8. 8/24ths is 1/3. One of those days? It happens. I don't know if I warned you guys last week that I'm dyslexic. It's actually kind of interesting. I'll pause the recording to the serious part of it. If you want to grab your big books from under your chairs, we're going to actually do here a little bit of what I call a workshop period, where we're going to do a couple of examples and then have you try some out of your book. I believe the correct page is page 50 or page 43. So you're page 43, 1 through 11, the odds. For each of those, I want you to rename them to the given name that they have for you. $43. Yep, the exercise is at the bottom. It should say equivalent fractions. Exercise, I think 2-4, something like that. The first one should be 1/2 equals blank over 16. Just do the odds for now. We'll give you a couple minutes and then we'll go over them quick. What's that? Wrong book. No, that's not the one. Yours looks different than mine. So. Got it? Thanks. So that book was interesting, but was it personal finance or business math? Cool. Good. Sure. Some of you are still working, and that's fine. It's either about half of you are done. So let's go over what you have done so far. If yours are a little different than mine, let me know, because my book is a little bit different edition than yours. So 1/2 becomes how many sixteenths? 8/16. 3/4 becomes 24. Good. 4 times 8 to make 32, so 3 times 8 to make 24. 7/8 becomes 28 30-seconds. Good. 8 times 4, so 7 times 4. 11/16 becomes 44/64. So good. 16 times 4, 11 times 4. 1/4 becomes 5/20. And 19/12, 114/72. Now later on, we're going to see how we're going to reduce that further. For right now, that's all we want. Now, some of these, sometimes we want to go the other way. We have something like the 5/20, and I want to turn it back into 1/4 or something simpler. It's what we call reducing. Bless you. Now up here, to get from 1/4 to 5/20, we multiplied both the top and bottom by 5. Here we're going to do the opposite. We're going to divide both the top and bottom by 5. 5 divided by 5 is 1. 20 divided by 5 is 4. Now we already saw that 1/4 and 5/20 have the same value. The key is looking at that and figuring out what can I divide both of those by. There's something, a little shortcut we have called divisibility rules. That has more than like 7 words, 7 letters. So it took me a while to remember how to spell it. Anybody tell me how we can look at a number and know quickly if it's divisible by 2? If it's even. In other words, the last digit is 0, 2, 4, 6, or 8. So I can take a number like 279,000. Let's see here. 540. That last digit is a 0, so that's even. That's divisible by 2. How can we tell if something's divisible by 3? Does anybody know? Well, it's not quite that simple, but it's a good try. 3 actually goes off of the sum of the digits. This is actually a pretty cool little rule. I don't, something this big, I'd probably just punch it in the calculator, hit divided by 3, and it'd be quicker. But what we do is you add the digits. So you got 2 plus 7, which is 9, plus another 9, 18, plus 5, 23, plus 4, 27, plus 0 is still 27. Is 27 divisible by 3? It is. If we didn't know, we could have done 2 plus 7 is 9. 9 is divisible by 3. So that whole number is divisible by 3. I punch it in the calculator. Comes out with no decimal remainder. For 4, it's not a big deal. There is a rule for 4, but it requires you to memorize all the multiples of 4 from 0 to 100, so it's really not worth it. Besides, if you divide by 2 twice, you've divided by 4. For 5, anybody know how to tell quickly? Last digits is 5 or 0. So is this number divisible by 5? Yes, it is. 6 is kind of the same as 4. I'll put it up here. It's actually not quite as bad. If it's divisible by both 2 and 3, it's divisible by 6. Well, we've already shown that this is divisible by 2 and 3, so it is divisible by 6. 7, there's actually a divisibility rule for 7, but it doesn't work for every number. It only works for really large numbers or numbers with a very small last digit. And it's really complicated, so I'm not going to show it to you. It really isn't worth it. you're curious, let me know, and at the end of class, I'll show it to you. For 8, again, like the 4, it requires you to memorize all the multiples of 8 from 0 to 1,000 for that one. We're not going to bother with it. For 9, just like 3, it goes off of the sum of the digits. Only instead of being divisible by 3, it has to be divisible by 9. Well, 27 is divisible by 9, so that whole number again is divisible by 9. How about for 10? It ends in a 0. Last digit is a 0. So obviously that's divisible by 10. For 11, there's a rule for 11, but again, it's not fun. It actually works for every number, but it's so complex it isn't worth it. We have the calculator. If you want to tell if something is divisible by 11, just divide by 11. And you can, no decimal, no fraction, it's divisible by 11. So we can use these in a number like, oh, let's see here, 51 over 57. You look at that and you think, well, those can't, there's nothing that divides into both of them. Obviously, it's not 2 because they're not even. It's not 5 and it's not 10. There's 3, yeah. 5 plus 1 is 6. 5 plus 7 is 12. Those are both divisible by 3. 51 divided by 3 is 17. And 57 divided by 3 is 19. So that reduces to 17 over 19. Now, we have been taught that you have to find the largest number. They call it the greatest common factor, which it makes it easier if you do, but we don't have to find that greatest common factor. Looking at 48 over 60 here, I see that they're both even, so that means they can both be divided by 2. What's 48 divided by 2? 24. 60 divided by 2? 30. They can both still be divided by what? 2. They're still both even. 24 divided by 2 is 12. 30 divided by 2? 15. Can we divide by 2 again? 15 won't quite work, will it? 15's odd, but they can be divided by 3. 12 divided by 3? 4, and 15 divided by 3 is 5. So we got 4/5. Now, if you had noticed, and again, some of you might see it, some of you not, both can be divided by 12. Good. 48 divided by 12 is 4, and 60 divided by 12 is 5. We get there in one step, saves a little bit of work. But if you don't see that right away, rather than sitting around trying to figure it out, it's usually quicker to start dividing by smaller numbers and just get there eventually. You'll get to the same spot. So in your book, if you flip to page 44, there's a set of problems there. Reduce those to lowest terms. I believe it again is 1 through 11 the odd. We'll go over those in another minute or two. Some of you are still working, but let's see how you did on the ones you have done so far. So 2/8 reduces to 1/4. Good. Both of them can divide by 2. 6/16 reduces to 3/8. Again, both of them can divide by 2. 90/80 reduces to 9/8. Good. They can both divide by 10. 7/28, 1/4. Good. They both divide by 7. That's one that I remember strictly because of football. 48/64 reduces to 3/4. Good. Both of those actually divide by 16. If you didn't see that, though, they're both even. You could have divided by 2. In fact, you keep dividing by 2. You do that 4 times and you get down to 3/4. 81/36. There you go. They both divide by 9 because it's 9/4. Well, let's talk about that. 9/4. A lot of us are uncomfortable with that. In fact, it's called improper fraction. And the term improper fraction is really not a great name for it because it implies there's something wrong with it. There's nothing wrong with it. In fact, there will be times where we prefer to have the numbers in that form. But if you go to visualize something, 9/4 isn't so bad. But if we have something like 44/7, so it takes 7 pieces to make a whole object, we have 44 of those pieces. If you try to visualize 44/7, it's tough to do. Human psychology tells us that the human brain can visualize between 7 and 13 things at once before things start to blur out around the edges. So you really can't visualize 44/7. But we can break it down because we know that it takes 7 pieces to make a whole object. We can create as many whole objects as we can. How do we know how many whole objects we can get out of that? Well, we could divide. We could try to do 44 divided by 7. If you punch that in your calculator, it's going to give you something like 6.2857143 approximately, somewhere in there. Don't worry, it's not contagious. I've done this stuff every day of my life for like 19 years, so you have to get good at it eventually, right? So it does tell us that we can get 6 whole objects out of there. It also tells us there's some pieces left over, but it doesn't really tell us how many. So perhaps an easier way to go about it, or a more informative way of doing it, is to actually do out the long division. Now you can still use your calculator to help you if you need to. We know that 44 divided by 7 is 6. Well, we need to know how many pieces are left. So 6 times 7 is 42. So the 6 whole objects used 42 pieces. We subtract, there's 2 pieces left over. So this is saying we have 6 whole objects, 6 whole objects with 2 pieces, or 2 of those 7s left over. We can do the same here. 9/4, we do 9 divided by 4. Yep, there's 2 in there. 2 times 8 is, or 2 times 4 is 8. There's 1 left over. So exactly 2 and 1/4. Come on. We might have 21/8. So we'll do the same thing. 21 divided by 8. 8 goes into 21 how many times? Twice. 2 times 8 is 16. How much is left? 5. So that's 2 and 5/8. Very good. So in your book again, if you take a peek at page 45 at the very bottom, yes. What's that? It's, yeah, 2-7. And I believe it is, was it like 11 or 13 through 25? Turn those into improper fractions. I'll take a look at your book, see what numbers they have. It is 13 through 24. So 13 through 23, do the odds. Change those into mixed numbers. I've got to dig up and see if I have an old version of this textbook anywhere. Yep, go for it. Let's see how you're doing on these so far. 14 fifths becomes 2 4 fifths. 63 fourths, 15 3 fourths. Good. 79 sixteenths, good. 4 15 sixteenths. 87 eighths, 10 7 eighths. Good. Now these last two, I want to take you through how to do them on the calculator because they're getting pretty big. I don't expect you to be able to do those in your head. But if we think of it as being 318 over 32, if we do 318 divided by 32, that gives us 9 point whatever. So we're going to keep the 9 there. So that means our whole number is 9. We need to figure out what's left over. So I'm going to multiply back. 9 times 32 is 288. Good. Then I just have to subtract 318 minus the 288 gives us 30. So that's 9 and 30 30-seconds. Now, if you saw that that could be reduced, bonus points to you. Both of those divided by 2 to give you 15 sixteenths. The next one here, 451 over 64. We'll do the same thing. So do the 451 divided by 64. Gives us 7. Then we do the 7 times 64, which is 448, yep. And then, of course, we can subtract to get 3 left over. So that's 7 and 3/64. Many of your calculators have a fraction function on them. If you have a Texas Instruments calculator, TI-30, it looks something like this, ABC. If you have a Casio or a Sharp, it might look like that, or, no, that's the wrong key, sorry. Might look like this, or sometimes it's a N over D key. There's a couple of different forms. If you have questions on your calculator, let me know. The graphing calculator, this is one of the weaknesses of that one. I teach a statistics course, and that calculator does everything you can do in that statistics course. Doesn't do fractions very well. You actually have the same version I have here. If you wanted to put that in, 451 divided by 64, and then convert that to a fraction, you can go to the math menu, and the first option is to change it to a fraction. Problem is it always changes it to the improper fraction. It won't give you a mixed number. So that's one of the weaknesses of the graphing calculator. Well, sometimes we need to go the other direction. We might have that 5 3/4, and we need to turn it from a mixed number back into an improper fraction. To do that, we need to take this whole number, which remember that represents the whole objects, and break it into pieces. How do we know how many pieces are in each of those whole objects? The 4, the denominator tells us. So we take the whole number, the 5, times the denominator of 4, which gives us 20 pieces. But we already had some pieces before, didn't we? We had the 3, so we add those to the 3. 3 plus 20 is 23/4. If I have 7 and 2/5, what do? 7 times 5 is, and then 35 plus the 2 is 37/5. Good. So if you go back a couple of problems, 1 through 11 there on that same section, are changing them from a mixed number back into an improper fraction. We'll give you a couple minutes, then we'll go over those. I know I'm cutting you a little short, but let's go over what you have done so far. 2.5 becomes 5/2. 1 5/8 becomes 13/8. 1 3/16, 19/16. Yeah, 1 times 16 is 16 plus 3 is 19. 4 9/32. Careful. 137. There you go. I wasn't sure if I was hearing you right. Now, you could do 4 times 32. You can use the calculator. 4 times 32, and then plus the 9 gives you the 137, and of course the denominator doesn't change. This next one, I'd do the same thing. 5 times 32, and then just add the 31. We get what? 191/32. The last one we're going to get 219/5. Again, you can just use the calculator. 43 times 5 plus the 4 is the 219. Okay. Starting, I believe it's either the bottom of that page or the top of the next page, bottom of page 48 or top of 49. Exercise 2.9 is word problems. Just have 1, 3, and 5. If you want to work on them, that'll be all your homework for the weekend. I wanted to make sure I gave you a few minutes for anybody who needs to finish the quiz. You can finish that up here quick too. Yep, if you're done with them, you can hand them in. Yep, 2-9. Thank you. The bottom of 47 into 48. Is it all? Let me take a peek, make sure I got the right pages. Okay, that is 40. Okay, I was off by a couple pages. So it is 47 through 48. Yep, just 1, 3, and 5 is all you need to do for that. In the big book, yep. That one. Yeah, if you're done with the quizzes, you can hand those in. I'll have those graded for you and back next week. Yeah, what do you need?